All right, 8.2, full stack auth. This is a fun lecture. Who likes fun lectures? Yeah, a couple of you, cool. The reason this is a fun lecture is because we talk about things to do with keeping information safe. And everyone seems to like that topic, you know? There are universals, I think, in the world of computer science. Like, people like a little bit of stuff that relates to security. People like a little bit of stuff that relates to user interfaces. I think it's just because there's some inherently fun things about them that kind of can make some of the more complicated parts digestible. But in this lecture, we're going to touch on very light topics around how basic security is an important step in building good software. Obviously, 1531 itself is not a security course. We do not go into an exceptional amount of depth when it comes to security, which is fine. There are lots of courses out there like that. If you're interested in these courses, you can go and study them. The kind of introductory course in that area would be COMP1531, 67741, 644, 6441, I think it is. Sorry, too many sixes courses. But you can go and learn lots about cybersecurity if you'd like to. It's also one of these topics where, you know, there are far more jobs in not cybersecurity related stuff than there are in cybersecurity related stuff, like always. However, like anything, the best part about what you can learn in your degree is to digest information from a range of backgrounds. You know, like I work in high-level programming day to day, JavaScript, things like that. However, I did operating systems at uni as a course, and it taught me a bunch of general knowledge about stuff that still helps me today, even though I don't really do anything and I'm not particularly expertised in that area. So a similar thing when it comes to security. Now, I'm just going to get up my animated slides, if that's all right. Because again, it hasn't changed since last term. I don't like the PDF things very much. Okay, so yeah, first question. This lecture is named Auth. It's a funny little name. It's meant to be a play on words because there's two things we loosely talk about in this lecture, which is the topic of authentication and the topic of authorization. Both start with the word auth. I don't know what auth is. Maybe it's a Latin word for something. You kind of get the gist of it. You kind of, if I said to you something like, are you authenticated or are you authorized to be here? You'd know what I mean intuitively, you know? Like, it's not like some totally wild concept. But if we try and nuance these two words together in a bit more detail, authentication specifically relates to the process of identifying who someone is. It's the process of going from, I don't know who you are, share some information with me, and now I know who you are and I trust that you are who you are, right? We all do this kind of thing. If you hop on a plane, you ever hopped on a plane overseas and you like hand them your passport, or you do that at the check-in desk and like whatever else? Same thing. You're a total stranger. At that point, a process happens, and now they know, they have an idea who you are, and they have a trust in that idea who you are. That's authentication. Authorization is a slightly different thing, which is about figuring out, you know, what your level of access is. So, you know, every time you got a student card, right? You try to tap. Has anyone ever just tried to tap on a random door on campus on the small hopes that you get into that room, right? And then you get that like awful do-do-do sound. It's like, what goes on in that process there is authorization, because if you assume for a second that the university has a model in their head that says, with your student card, you know, they like, if you have that student card, we trust that you are who you are, right? Like if I gave you my staff card, then you could tap into all the things that I could tap into, right? So like having that card is the equivalent of being that person at UNSW, right? Authorization is every time you tap, the uni tries to figure out who has access to those rooms, right? Are you authorized to do that? So it's not really about determining if you are who you say you are as much as it's like, based on the person we understand that you are, what are you allowed to do or not do in this particular scenario? You don't actually have a lot of this in your project. There used to be a little bit in the old project, but this project, there's no real idea of like a user logs in and they have particular like rights or, you know, not rights. But a classic example would be like Microsoft Teams. You can't delete each other's messages in your team, right? Like if you post a message and then Sally posts a message and then the third person is like, I don't like those messages, they can't delete them, but your tutor can, you know, because your tutor is an owner of the team that you're in on Microsoft Teams. And therefore, when a tutor tries to delete something, Microsoft has to check, is this person authorized to delete this based on whether they're an owner or not. So that's authorization. I just kind of gave some examples already. You'll see a lot of these things in the slides here that we don't talk to. A lot of the times they're in the slides because we know you all kind of glance through the slides later on and you don't want to watch the recording, which is fair. I wouldn't want to watch recordings. So now we're going to talk about authentication, which is the primary part of this lecture. We don't really spend much time on authorization because there's not actually a lot to figure out there, right? Like, you know, if someone tries, you probably get this as you work through the project. If someone tried to, you know, delete something and you know they're a valid user and you just want to check if they're an admin or not, you know that's just a series of if statements and checking stuff in the data store, right? Like, it's a concept. The implementations of that concept are not particularly complicated. But authentication is a little bit more complicated. So what's the most basic approach when it comes to storing usernames and passwords? You follow 3 steps. First step is that the user registers. We store their username and password. When a user goes to log in, which I'm sure all of you have tried to have happen before, what do you do when they go to log in? You compare their input password against their stored password, right? I'm sure that's what you do right now. You say like, yeah, data store, get that email address, check if the password equals the input. And then if they match, you know that they entered the right password. So that is in and of itself an authentication process that you have. That's not to say it's not authenticating. It is authenticating the user. And it probably looks something like this. I know the code's a little bit cut off the screen here. I don't think I can do too much about that at the moment. But here's a little piece of, maybe I can copy it all or something. It's because if I make it sideways, there we go. Just hide that bloody face of mine, Jesus. Here's a piece of code, authenticate simple. We have a data, this is all TypeScript up here, nothing particularly new. This is our data store, or the mock data store, and then we've got our register and login functions. Does this look like what you have currently, roundabout? Maybe you've got a slightly different implementation, right? But login's like, you check if the email's in the store, and then you check the password. Yeah? Okay. What's wrong with that approach? What's the downside of it? What many of you have done? I'll bring it back up on the screen. What are some? Oh yeah, sorry. Yeah, exactly. So the passwords are just sitting there in that data store, and even more specifically, if you have implemented persistence, they're sitting there in an actual file on the file system sometimes, you know, like your database.json. So you think about it for a second. Imagine this was like a production scale application. You now just have a JSON file somewhere with all the passwords in it. Now, granted, a production scale application is not going to be using JSON, right? It's going to be using some database like an SQL database or a Firebase or something out there that stores data. But it's the same thing. It's all going to be stored in what we refer to as plain text, which just means unhidden. It's just sitting there as text. And you know, do you ever have that? I mean, clearly you have, but like, you ever have that moment where you open your database.json and you see a bunch of passwords there? And you think about it for a second, and you're like, that's a little weird, you know? Shouldn't be able to kind of see passwords. So that's what's kind of wrong with it. So we're storing these people's passwords. Now, if you didn't store things persistently, you could argue it's not too bad because the data store exists in RAM and it's never actually stored anywhere. Sure, just because that question comes up a few times. But regardless, nothing is ever really just stored in RAM anyway. It always gets stored somewhere. So we think about the persistence case, and we need to figure out a way how to hide the password, right? So hiding the password is fairly important. But what does that even mean in terms of hiding the password? So we got to take now a step back, and that was about the project. This now is about actually how we hide information. So there are 2 words that are important to digest. It's the word encryption and the word hashing. Encryption and hashing are both words that contain processes of taking plain text information and concealing it by turning it into something particularly random. Now, everything on the left here is what we call plain text. It's just text as you and I read. And what we can do is we can take this plain text and we can shove it through what we call a cryptographic function, which is, you know, I always think about like if you want to imagine a cryptographic function in the simplest sense, let's imagine you have a string here like hello, right? And I don't know if many of you would have done this in high school. I don't know what's in the curriculum these days. But you could write this isn't a cryptographic function, but you could write a function that tries to hide data by simply going, well, let's just increase each letter by one space in the alphabet, right? Like I is after H, F is after E, M is after L, M is after L, P is after O. Is that right? Hopefully that's right. So like I could have a function called my hide function that takes in a string, and it just increments each by one character, and then it outputs this. So, let's imagine that you're talking to your friend on Instagram and you're sharing all of your spicy memes or something together, and you're like sharing, I thought that was funny. And you're like, I don't want people to know that was funny. I want to encrypt my message that I think it's funny. So you would just pass it through this function. All the characters would change slightly. And then to an innocent bystander like me who's reading your message, we'd have no idea what you're talking about, right? Like that's the fundamental idea of hiding information. It's like changing the structure of it so that it looks like this, but in actual fact, it means something else. Difference is with cryptographic functions, these things are extremely complex. And more importantly about cryptographic functions, it's very difficult to take something on the right-hand side here and turn it back the other way. Because in this kind of trivial example I gave, if you understood the function, if you got the source code for the function, what you would be able to do is you would be able to take something like that and just say, well, that's really easy. I'll just do it the other way around. I'll just go back a space in the alphabet. I'll go back to H, and then I'll go to E, and then L is before M, and then L is before M, and O is before P. Oh, I uncovered your message, So real cryptographic functions are significantly more complex than that. And again, their key aspect is that they're basically one-way functions a lot of the time. There's a whole bunch of mathematics behind that, because you've got to remember, at the end of the day, cryptography is a topic, which is the topic relating to how we can hide information and stuff like this. It's mathematics, right? Like a lot of things. Same with machine learning and artificial intelligence. The people that pioneer all of that stuff, they're all mathematicians. It just happens that once the math gets pretty stable, computer scientists come along and think, oh, well, we all understand the math now. Maybe we can write some computers to do the math for us, and then we have some stuff, So all of this is rooted in mathematics. There's a course, I don't know if it exists anymore. I took it like 8 years ago when I was studying or something. But it might, is it there? I don't know, maybe it's not. They probably changed the name of it. I'll try and dig it up for people. Oh, is it? Oh, it is here. Okay, Math 2400. Does anyone here have to take discrete maths? Yeah. Is it just soft-eng people, or is it comp sci too? Do comp scis have to take it? Yeah. Everyone has to take it. Cool. So the only prerequisite to it's like math, that's discrete, I think, from memory. Anyway, the point is that this is a course that, if anyone was interested, it basically goes into like a lot of that detail of how that stuff works. Because when I say to you like, oh, there's a function out there where you can take a string and it turns it into this thing, but it's literally like impossible to take it from the output back to the input, it makes your brain go like, what is that? That doesn't make sense to me. Like the idea of an irreversible function doesn't make a lot of sense. Because we kind of think about high school math. If you square a number, you can just square root the number. If you multiply it by 3, you divide it by 3. If you add 3, you subtract 3. So, but it's all to do with that. Some of you probably heard of it. The whole idea of like, if you multiply, it's really hard to find prime numbers, prime values of a very large number. It all gets into that kind of topic, and I'm not really going to talk about it, not only because I'll butcher it, but also because it's not strictly relevant. Because the point is, there's functions that take in random inputs and they output stuff. Now, one of the most basic types of these functions is what's called an MD5 hash. MD5 was a really old function, and I mean, maybe I can find it. I've never actually tried to do this in the lecture, so maybe it's like, yes, this is, I haven't tried to look at this in a long time, but this is obviously not JavaScript, but this is like an example of the function that takes in a string, right? Gibberish to me, right? It makes as much sense to you as it does to me, realistically. Like I'm like, oh, that looks like programming. Okay, mod something, message extend something, less than, dot less than, now I'm scared. You know what I mean? Like it's a bit of gibberish, but this is what takes in something and outputs something that can only go one way. One of the oldest forms we had of this was an MD5 hash. MD5 hashes were quite straightforward, and they're actually quite important for a long time. What I mean by important for a long time was like they were used quite commonly. When I first started doing web development a long time ago, people were actually using these to hide information. And just so it's less abstract, let's say I have a secret. What I can do is this website will just pass my string through an MD5 hash function, and it will output this. So that's my kind of like gibberish output here. And the point is that no one can take this and pass it through a function that gives me back to this. Or more specifically, the functions that would be required to do that would take a virtually infinite amount of time, you know, like thousands of years.
Will it generate the same code again, or is it?
Yes, it's totally deterministic, which is a really important part of it too.
Okay, because if you can't go back, then it doesn't really matter, right? Like, it just makes the same one every time.
Yeah, exactly. Exactly. So yeah, we have that. That's an MD5 hash. That's not really used anymore because it's basically become insecure now, which is an interesting question around, this is all background, by the way. This isn't like heavily assessed in 1531, this specific stuff. How did it become insecure? Well, what happens over time with this stuff is that what people will do is, let's imagine that you go back 15 years on the internet and you know that passwords are stored this way. What people start doing is they say, well, what's the most common password in the world? It's password. They go, okay, well, that's that. And then what they do is they go and copy this down into a table here, and they just write that down like that. And then one of the most next common ones, like password 123, and then they just copy that down. And people basically build up these big databases of what this string is to this hash. It's essentially a form of what you would call like brute force, like reverse engineering or something like that. You're just kind of doing it the manual way. But there's no function that can get you that. Do you know what I mean? So like from a hash here, you can't actually go and take that and go back to this string. The only way you could do it is if you've started always from the inputs and gotten every possible input and generated all of their outputs and then just correlated it up like that. The problem is this takes an exceptional amount of time. That's where this becomes problematic, because you think, oh, well, that's easy. I can write for loops, right? Like, you know how to write a for loop. It's pretty manageable. Well, then you get into the problem with, let's imagine that an MD5 takes 0.001 seconds to calculate, right? Because it's still a math function. It's got to do something. It takes clock cycles on the computer. So that's 1 second for that. Well, you think, okay, well, a single character password that can contain, say, letters and numbers, uppercase, lowercase, might be 60 possible characters. Or actually, with all the exclamation marks and whatever else, let's just make it 80. I don't know the exact number. So you think, okay, well, if I can have a single digit password with any of those 80 characters, that's 80 possibilities. Sure. So that's going to take 0.01 seconds times 80 for me to calculate all that and put it in an Excel spreadsheet. Well, that's naturally going to be 0.08 seconds. That's pretty quick. So then you think, oh, well, I wonder how long it is to do it for 2 character passwords, right? Well, for 2 character passwords, high school math, how many possibilities are there? It's like 80 squared, right? Because you've got 80 times 80. Well, now what happens is, what's 80 squared? Well, it's 1600. So then you think, well, 1600 times by 0.01, that's now 1.6 seconds. Right? And if I do this of a similar thread. And then you can kind of take this further and further on, if you'd like to, where I say, well, let's do 80 to the power of 3. Well, now that's going to be 512 seconds, which is what? Like, how many minutes? 8 minutes? Okay, you get the point. I'm not going to do this all the way up, but now we've got that many minutes, so that's 11 hours. So now you've got like a 4-character password is going to be 11 hours, and so forth. And what you get up to pretty quickly is an 8-character password will be that many hours, which is for a computer or whatever, it's like 53,000 years. Now, naturally, computers can do this kind of stuff probably way quicker now, right? Like way, way quicker. So I don't think that's indicative by any stretch. But the point is that This is why we talk about long passwords, is because if you have a 12-digit password and you divide that by 1,000,000 years, that's now looking at like 2,000,000 years to calculate all of that, right? So when we say, oh, you just make an Excel spreadsheet with all the passwords and their respective hashes, it's like, cool, that makes sense until you actually break down the mathematics of it. And this is all because it's essentially an exponential problem, right? Because the search space of a password increases exponentially every time you add a character. That's kind of the background of it. So the point is that we have these functions that are able to go from one value to another. Now, I mentioned at the top of this slide that the topics around hiding information are both relating to encryption and hashing. Encryption is slightly different. What I've been talking about here is the concept of hashing. It's just one-way movements of information. Encryption often uses hashing principles, but they do it in such a way that you can actually go back to the original value if you are like a special person who has like the key, if that makes sense. So you kind of imagine hashing as like, I'm going to create gibberish from my information and I'm going to throw away the key. No one can ever, figure out what that is. Whereas encryption is more like, I'm going to take my information and hide it. I'm going to make it gibberish, but I've got a key that can bring me back to the first place. And that's a whole other more complicated bucket of stuff. That's all to do with SSH keys and things like that. At the start of the course, when you generate an SSH key and you like copy it into GitLab, there's like public, private keys. And that's, again, a whole other topic in and of itself that is originally rooted in mathematics and, relates then more to computer science nowadays. So we're not really talking about encryption. The process of hiding information and then being able to unlock it, that's not really to do with the course, but it relates to hashing because it uses hashing in that. We're just specifically talking about hashing. And this is, again, encryption is reversible, hashing is irreversible, but encryption does use hashing to power it. Reversibility does make the hiding process finitely less secure. A good example of that is that I don't want to oversimplify it too much. I'm not a big Apple user, but does anyone know about how Apple's if you unless you change your setting, if you forget your iCloud password, Apple's we can't get in, we can't help you. Once you forget your password, you're screwed. I think they allow you to change that if they want, but maybe I don't know, but they set that up in a way because they would have done something much more thorough than this. But my point is they literally went out there and were like, we're going to hash your password and we're going to use that to kind of hide all your data too. And if you forget your password, we're we can't do anything at all. They obviously have what your information gets converted into that's gibberish, but because they've hidden it all away from you, it's the same thing. They've hidden all your information in a somewhat irreversible way that you can only kind of reverse with your password. That's actually a lot more to do with encryption, so I don't want to kind of mess you up there, but I'm trying to get the concepts across to some extent. But let's explore an example, because this is kind of heady. This is a piece of JavaScript code here. A very simple piece of JavaScript code. It imports one library, which is called crypto. It's the crypto library. And we have a function called getHashOf. There's not much more information on that line at the end there. What you'll notice with that particular function, though, is that it's got a whole bunch of gibberish, but if we forget that function for a second, we have a secret message called a message called Big Mac secret source. And then what we do is we get a hash, another string, which is simply the result of calling a function and passing our string in. So this is our plain text information, Big Mac secret source, and this is our hidden information, which is the gibberish hash, like that MD5 hash we saw before. And then we're just going to print out our hash there. Now, in this particular case, what this function's doing is it's using the crypto library to create the hash. Now, it's a little bit weird. What it's doing is it's getting the library, and then it's creating a hash capability. It's creating that cryptographic function. This particular one is kind of the standard one these days, which is called SHA-256. That is like MD5, except much newer, because MD5 everyone kind of built out. The MD5 was such a simple function that everyone built out those tables really quickly. The processor could do it like that. That's why it's not used anymore, because everyone knows every MD5 password now. But this function's far more complicated, which means it takes computers way more time to calculate it, which means to do it for the billion trillion passwords or whatever there is, it takes like literally forever. And then what you do is you basically feed your plain text piece of information into that cryptographic function. And then this digest text thing here is, I think, just to do with the fact that by default it kind of comes out as a byte stream, but you want to get it as hex. And like, well, don't know why that didn't open. But yeah, here, like if I type in hello, you'll see that like this is a hex string in the sense that like it's only, if you look at it carefully, it's only made up of 1 zeros A, B, C, D, E, F. So this digest hex part here is just saying, look, I know you're just going to want to give it to me as binary, but can you actually give it to me as like hexadecimal? Because that's kind of how a lot of people digest it. Hexadecimal is easily represented as a string. So that's that function that we write there. And then if we call it get hash of, we'll convert Big Mac secret source to that. Now, I'm in a bit of shambles this morning because, again, my laptop died, so I grabbed this one literally this morning, and I have nothing set up on it. But if I really quickly, I'm going to see if I do have any code floating around from last term that I can quickly. Has anyone used WebVLab before? It's a great thing to use in a pinch, right? It's a horrible experience, but like if you're like, oh, I need to do something quickly, it's just a bit slow and a bit awkward, but it does the job. But if you just search up WebVLab, then you get it. I should have last term's stuff here. Great. That's good. Yeah, so I've obviously got this information sitting on VLab, so I can keep talking to you about it. I've got this file here called hash.ts, which has all that stuff in it. Naturally, it's gone and got a bunch of extra stuff in it, which isn't ideal. One of the problems with WebVLab is that you can't really copy and paste and do a few other things as easily. I'm just going to get rid of a lot of stuff. There we go. Big Mac secret.
So is SHA-256 just like one of the encryption libraries that the crypto thing has?
Yeah, it's a cryptographic hash function. And yeah, there are others. And they basically just vary in their complexity. Because obviously, like, if a hash takes a while to calculate, then it's going to be slower to get a result, which might leave for a bad user experience. But what it does mean, though, is it's really hard for people to build out all the versions of it. Because if it's like 1,000 times slower than the other ones, it's just going to blow out. I mean, someone asked me, I think in a previous term, they said, so MD5 is dead. And it's like MD5, the reason, again, it's like I'll show you. If you go like MD5 rainbow table. So if there's like an old website out there that uses MD5 to store a password, the point here is that if you enter a hash, like if you're like, my password is going to be like happy pancake, which is not a bad password by any stretch, right? It's actually pretty long. It's like 12 characters. It's the recommended length easily. Wow, it's actually 12. That was a guess. If I kind of put this in my... If I put this in here, I don't know if it'll work. Yeah, that one won't work. But if I maybe try like happy panda. And then this is going to... Has anyone ever gotten caught in a loop? Like, I feel like I had this bug once a month ago. I did like literally 100 of these, and it just wouldn't let me through. But the point is, so there's someone out there who has a big Excel spreadsheet of all the hashes and stuff, and you can enter that and you can get the original result, right? Just because they look it up in the table. But the thing is, even though MD5, no one uses it because it's quite dangerous, because if someone enters a password like happy panda, which isn't a particularly easy password, you can still guess it. MD5 is actually used for its deterministic benefits. So like a common example, you might say, has anyone ever seen on a website where they say like, download this file and then they say like, check the signature or something? Has anyone ever seen that? Yeah, so basically like when you download, like let's say I go to a website, like I'm trying to think of a good example, like WinZip. I don't know. I'm just thinking of a random, like WinRAR. It's like a file for like zipping things up, right? And you'll go to a download page of these websites, and I don't think this website will specifically do it, but they'll have a particular file to download here. And what they'll sometimes say, not sure what a good example is, what they'll sometimes say on the website is they'll give you a little hash, like an MD5 hash, and they'll say, this is the MD5 hash of the file. And what someone has actually done is you think about like, oh, well, I can obviously use these functions to convert strings to a gibberish. You can actually pass a whole file into an MD5 function, and it'll just like read it as a string, and then it'll output something. And it's actually it's a tool that's used quite a lot to kind of verify if like also integrity of things. Like, has anyone ever had like a video file on their computer or something, and they've had it for a few years, and then randomly it doesn't work anymore? You try and open it, and there's like an error, or like anything, any file that's ever gone busted. One, I'm not, again, I would have had this set up for you last week. I don't know if we have it. Yeah, MD5 sum. So let's imagine I have this file called hash.ts here. If I think this will work. Basically what this is saying is that if it takes the entirety of a file, it's easy to imagine because it is a string, but every file on a computer could be turned into a string. It'll just say that's the MD5 hash of that file. And then if I literally change anything about that file, like I put a little space at the front there, and then I run that again, the hash is different. Notice at the end there. So MD5, whilst it's insecure, isn't really used for security reasons that much anymore, like security purposes. But the irony is because it's such a fast hash, which makes it insecure, it's actually really good for non-security purposes, where you want to kind of just deterministically turn a string into a random set of things to say, well, this is like it here, and I could check later on if anyone's modified that file just by using that hash in that particular case. So that's again very tangential knowledge. Point is, we were having a look at this piece of code, and we got distracted by my shenanigans. That's the code there. It's just the stuff we were running on the slides. I'm not 100% sure if I've got npm installed, but let's see if we have. It's not installed. OK. Gotta wait for npm now.
You just turn a file into that hash code.
Yeah, because I mean, yeah, I mean, you can turn anything into a string if you try. So yeah, you could feed anything into the function, and it will just spit out a value, if that makes sense. I actually did that recently because I was doing this big backup at home. It was kind of one of my rare nerd out moments because I don't really do that many nerdy things. And I copied like 4 terabytes from one hard drive to another. And it was like 10, you know when you copy, do many copies at the same time, you got that big list of files copying. And then I woke up and the hard drive had crashed overnight, and I had to copy the rest. And I was like, God, I don't know if all my files copied okay, and I'm not too sure how to check. So all I did was I literally just grabbed a thing off ChatGPT, pasted it in the terminal on one hard drive, and it went and found all the MD5s of all the files on one hard drive and another. And I found 12 files that had been corrupted while copying. You know, and this is exactly what lots of if anyone's ever got backup software or things, they do the same thing. They don't just look at the file name. They're like, oh, that file name's that file name, that'll do. They'll go and actually hash those files to a string and be like, well, the only way those hashes are the same is if the files are exactly the same in terms of every single little bit. There's obviously a once in a trillion example where 2 hashes collide, because naturally if your function takes in strings bigger than the size of the hash, it just has to follow that there will be what we call collisions with the hashes sometimes, you know? Because if the input space is bigger than the output space, there will be collisions. It's just everyone in the world considers the fact that a literal once in a trillion collision is fine, you know? That's just kind of called handling risk. So if we look at this, I just npm installed that. I run this TS node permission denied. That's weird. Odd. I haven't seen that error before. Maybe I can just run it directly. Just try it again.
Not authorized.
Yeah, exactly. Not authorized. Let's try it now. Okay, seems to work. So that is a SHA-256 hash of Big Mac secret source. And again, it's important to remember that if I was to change this ever so slightly to something different, like Big Mac secret source, capital E, right? Like that. A change ever so slightly to that would create a virtually indistinguishable hash, you know? So this is like, it's seemingly truly random. And again, it is obviously deterministic, but it's not possible to take that. Even if I got something relatively simple, I couldn't go back the other way. So that's like hashing in a nutshell. Now, how would we apply hashing? This is coming full circle now. How would we apply hashing to our login and register functions? This is not the answer. This is me showing you the code you probably have written yourself. Yes? Storing the hash instead of storing the password. Okay, that's a great point. So when you add it to your data store, instead of storing Big Mac secret source, imagine that's my password, you store the hash of Big Mac secret source, which we know we can calculate in JavaScript by using that function. So we store that instead of Big Mac secret source. However, when I come to log in and I give you my input of Big Mac secret source, how can you compare that to the hash? Because like you have the input now. Yeah, exactly. You hash the input. So it's one of those things where like I find like a third of students get that straight away. The other 2/3 need a minute, and then they all get it straight away anyway, which is you would take this piece of code here and pay really close attention to line 20, right? When we're comparing the passwords right there. What we do, and I've highlighted the lines for you, is instead of storing the password in the data store and then comparing the passwords directly to the great comments of the people in the class here, we simply hash the password and store that in the data store. And then when we fetch that hash from the data store, we compare it against the input hash. And this is how virtually all companies store your passwords. You know, anyone that should be in business at least. There was a time maybe like 10, 15 years ago where you would go to reset your password, and a few companies would like send you your password in an email and be like, has anyone ever seen that before? Maybe a website at some point in your lives? Yeah, super unsafe. So that maybe used to happen a bit, but obviously as like things go wrong for companies, they figure things out more. So this is how everything's stored now. And that's why you can't get your password from companies most of the time, because they don't know what your password is. You know? Like they literally don't know. They have hashed your password. They know how they generated it, but they don't know what your password is. And they don't want to either. Like no company really wants to know your password because they already have access to your data. You know? Like what's your password going to do most of the time? The point I was making with Apple before is Apple's obviously going to hash your password, right? Like everyone does. But what Apple does even more than that is they actually then encrypt all of your data using your actual password, not the hash of it, that way as well. So quite often when it comes to encryption, your password is not just like something that's hashed, but with encryption, it's also the key that's used to unlock your data as well. Because there's a much deeper topic around encryption, which is where you can randomize data, which again, only with that key can you undo it. Back to those SSH things. If you're curious about that topic, you can Google public-private keys. This is a great little topic. It kind of shows you how again, this takes more than 10 seconds to digest, but it basically shows you how the topic of encryption is essentially encrypting something which is obscuring the data in a way that can't be reversed. So it uses that hashing, but there's keys that you can use to unwind that, right? But again, we could do that with passwords. In theory, a company could encrypt your password, if they wanted to. where like it was super hidden, and if someone broke into the company, they couldn't find it. But the problem is when you encrypt something and make it reversible, there's always a key out there somewhere to undo it. So even though the risk is significantly minimized, just from a risk management perspective, you would never ever, like, do you know what I mean? Like if there was a room that you never needed to go into, you would never keep a key to it. It's just risk. And when it comes to a password, because a company never needs to know your password, why encrypt it? You would hash it instead. And that's kind of the rules around when you encrypt or hash stuff, is that if you never actually need to use the value, if you never need to know what it was, then you hash it. But as another example, let's take, let's take Instagram, or where do people message these days? Do people actually still message on Snapchat? Is that a thing? Instagram? Yeah, okay, there we go. Figured it out. When you message on Instagram, they don't hash the messages you send, they encrypt the messages you send, because like they need to see it at the other end. Like even if they don't need to see it, like maybe that's not the best example, whether they need to see it or someone else needs to see it, that's more to do with encryption. Maybe messages aren't the single best example, but yep, so that's what we do. This lecture is actually quite straightforward because it's basically a 1-hour spiel about encryption that asks you to go make a 5-line code change in your code base, right? That's what it's about. It's just that it's important to understand what you're doing. Because we could just say to you like, oh, go do this and it makes it gibberish. But back to my initial point, if all we said to you is that there's a function out there that makes your code gibberish, you would come back sometimes and think, well, I could write my own, back at the start. I could write my own, just change some ASCII characters. I don't need all this fancy stuff. But again, that isn't hashing. That's it's something very reversible. Now, this is important topic for iteration 3. A question: can we use this? Can we use this topic for tamper-proofing things? And this is a funny thing because it's kind of similar but a little bit different still. Tamper-proofing is a funny idea. So let me take you through it, and this relates to iteration 3 as well. In iteration 1, all of your functions returned an auth user ID, and they took in an auth user ID. Great. Wasn't the best idea, so in iteration 2, you introduce sessions. Now, when you have a session ID, right, whose token just has a session ID in it? Hands up. Whose token has a session ID and a user ID in it? Hands up. OK. More people. So let's imagine a user ID is 1 and a session ID is 1. Now, help me out here. Put your hand up if your session IDs are generated, or user IDs are generated just incrementally. Like they start at 1 and go to 2 and go to 3. Hands up. Put your hand up if they're random numbers. OK, cool. So this is where things get kind of interesting, because in the cases of incremental numbers, and this is also kind of true for random numbers to some extent, though much less, what can happen is, imagine for a second that because all of your servers work with the web browser, right? Like that's how they will work. They work with the front end. Most of you have probably tried the front end a little bit in iteration 2, even if you didn't spend a lot of time with it. So what happens is, as a front end, I send a login request to the server. I give my username and password to the server. And then what the server does is it sends me back a little token, and that token contains a session ID and a user ID, which I can see, right? Now, you can't hash the token. Well, I mean, you can hash the token, sorry. That's not the right word. But let's imagine that me as a user, I see this, and what I see inside the token here is I see these 2 pieces of data. What I can do if I'm a bad person is I can start playing around with this information if I'd like to and change it up. As a good example here, this course website, let me see if it works. This course website, if I pay attention to the data that is recorded from the server, let me see if it's there. Why is it not there? I would have thought it's there. Cookies? Yeah. See this here? there's actually a piece of information on my computer here called ZID. Now that's my ZID, right? If I wanted to, I could try and change that to another ZID, some random ZID, 525-545. Yeah, that's close enough to probably what one of yours is. A lot of 5.4s these days, is it? What does your ZID start with? 5.5. Oh god. Okay. Also, you know what I hate? They went from like Z34 to Z35 and then straight to Z50, and I always hate it because like it makes me seem really old because they just like skipped like 16,000 numbers or something. So I could change it to that, and when I refresh this page, what actually happens maybe is that the web browser now sends a different ZID to the server. This is me trying to tamper with information on my browser. So that's not going to do anything wrong because the course website is better than that. But the point is that when you send back a token to a web browser or anyone, they store it, and someone might say, you know what, I wonder what happens if I change my session ID to 2. Or you know what, I'm going to pretend to be user 2, and I'm just going to start making a request to delete a quiz with session ID 1. That won't work. There'll be an error, right? Because you'll catch that error, because it's probably not a valid session for that user. Then I'll send it with 2, then I'll send it with 3, then I'll send it with 4, then I'll send it with 5, then I'll send it with 6, right? So you basically send it with all this like different kind of data, and we tamper with the information. The topic here is around, are there ways to tamper-proof our data? There's a couple of ways to do this, and it's worth exploring them. So one of the first ones, there's an easy way that's like good enough, and then there's like a good way that's harder to understand, but it's still kind of useful. The first way is to obscure the session ID or the user ID if you'd like to with a hash. And what I mean by that is that and this is not great, is that basically like how some of you generate random numbers right now? It's basically the same thing. It's just that for those of you who are generating things incrementally, like 1, 2, 3, 4, 5, for iteration 3, you could change that to random numbers, or you could just hash the numbers themselves, right? Like hash 1, hash 2, hash 3, hash 4, hash 5, hash 6. Neither of those are perfect solutions. The reason they're not perfect, and what I mean by that is like, let's just say I have an ID of 6. That's my user ID. So I just send them back a session ID of that, and I store that as well in my data store. So now when I have my data store here, which has users, which is a list or something, and then I've got like user ID 1, and then I've got like my session IDs here, I just stored that instead of like 1 now, Now, using a hash there is really just a glorified way of using a random number, right? In the sense that all you've done is make it really hard for people to guess. You've created a barrier. It doesn't prevent problems, but it certainly slows people down, right? Because, well, with a random number, like put your hand up again if you did the random numbers. Okay, how many digits is it?
I think 6.
6, okay. So 6 digits. That's going to slow someone down a lot, right? But it's still only 6 digits, right? But that's also, so they're going to have to try 100,000. They would have to try 100,000 different possibilities. That is, in some scenarios, too bad. A lot of servers, if someone tried to do that 100,000 times, they just like cut them off, But on less complicated systems, that simply makes the problem 100 times less risky, which is still finitely risky, right? Using a hash is the same problem, because if someone's smart, they'll just go and dump those hashes into like these rainbow tables and then be like, oh, well, that's just the number 6. All right, well, they're clearly just like hashing a number, so I'll just like go get the hash of 7, and then I'll just pass that in anyway. You know what I mean? So like it's still barriers. It's still like a lot more effort. Someone really has to sit down, right? And a lot of systems and their security, they're a product of like, if someone wants to break your system, how hard they're going to try to break it is going to be based off how valuable your system is. so at the end of the day, if you have a really valuable system, someone will actually spend 2 days trying to mess around with it, you know? Like with the course website, there's a couple things that you probably could do to ruin it, but it's like, we know you're not going to bother because there's nothing in there. Like the most you can do if you log into the course website is see another group's runs. If you could log in as me, that's what you do. You'd be able to see everyone else's run data and submit a run on behalf of them. So like, we don't spend hours and hours perfecting it because we know it's safe enough. And the point is that, you know, maybe that is safe enough, but there's still a finite risk there. You had a question, yeah.
What if we hash the hash?
What if you hash the hash? Yeah, that's, again, what you're doing there is you're taking the risk from like 1,000,000 to 1,000 with the first hash, and then from 1,000 to 1 with the second hash, because what you're hoping is that someone doesn't just think to like rainbow table that again. Because someone could take this and say, I wonder what this is. But also this, to your point about hashing a hash, this is also tricky because this actually won't come up because it's, oh, it does. Wait, did I copy the right thing?
Yeah, it says MD5.
Oh, yeah, exactly. Yeah, so I didn't even know they do that in the rainbow tables. So that's super interesting that they, I guess, yeah, they just hash the hashes and they store that as another column or something, right? So like, it's tricky. One thing people do sometimes, and again, this is all getting pretty random, is they'll store basically, they call it a salt. It's a chunk of information beside it. So let's imagine that what I hash is not just the session IDs, the incremented session IDs are 7, but I hash 7 followed by, I really like pancakes, something like that. And what that means is that like you're going to make the hash you're going to make the input super long, because the longer the input is, the harder it is for people to guess it, because I don't know if this has been looked up, that one isn't in the table because it's such a long input, if that makes sense. So that's another way you could do it. But again, all you're doing is kicking that problem down the road a little bit. You can do that in iteration 3 if you want. We just want to make sure that you've taken a step that you can explain to your tutor to sufficiently obfuscate that information in the token, right? So that if someone sees that, it's really hard for them to tamper with it. So when we say tamper proof in iteration 3, what we really probably should say is like extremely tamper resistant, because, you know, there are better solutions. But let's quickly talk about the better solution now. I'm sorry for kind of talking pretty quick. There's just kind of a lot I want to chat about. The second one is signing our payload with the hash to help us understand if someone has tampered with it. This one is a really interesting concept because it uses hashes in a different way, and it's similar to that example I showed you with the file system. And the different way that it does it is, so like, let's keep our hash function here. And then what I'm going to do is I'm going to create a token. That token is going to have session ID 1, and it's going to have user ID 1, like that. OK, now we could try and hide that information from the person if we want to, you know, like we make it random number, hash, whatever else. Or another thing we could do is, what if we actually, for a second, got a token string, which is just the JSON, stringified JSON of the token. And let's first print that out. And you should be familiar with this because you know that your server, right, when it returns the token, it returns it like this, because it has to JSONify it and send it out. However, what if we decide to, because then you think, oh, OK, well, what if we hash that, or we hash the session ID or something? Sorry, my brain just had a moment. There's a few different ways I could do this with you. OK. I'm going to unwind that for a second. So we've got our token, and we have our session ID of 1 there. Maybe let me just break this out so it's a little more like this. So we've got our session ID of 1, and you know that if I call get hash of session ID like this, which is a number, which it's going to want it as a string. Did we turn a number to a string? Is it just 2 string? Can't remember. Oh, sorry, tokens, oops, yeah. So if we take our session ID and we hash it, we know we get that, sure. But all we've done is hash the number 1. We've established that's not good. However, what happens if I hash the number 1 alongside a secret password like that I like pancakes we saw before? So let's now create a secret, and that secret can be something super long, which is like, I won't drive to UNSW again, like that. So what I do is I just slap it onto the end, like this. Many different ways you can do this. It's just like one way. And now what happens is when I hash this, I get this output. OK. But now what I'm going to do, because I'm a little bit sneaky, is that, sorry, let me just break this code up a little more. So we've got our session ID, and then we get our secret, and then I'm going to call this my signature. We get our signature, which is our hash of this. What I then do when I return this to the user is I give them that signature in the payload. This is where things get a little confusing. That's why I say it's the harder one. And we don't expect you to do this. It's just fun to talk about. So what this means now is that when someone, console.log, when the token gets returned, when it gets sent back to the front end or the API client, it actually looks like that. But what's interesting about this is that this signature, if let's imagine now someone tampers with the data. Okay? So what I mean by that is let's say a separate piece of code. If I come back in here, if I just comment out all of this for a second, right? So forget all of that. Forget all of that. Someone has now just sent us a payload that looks like this, input token. Does that make sense, right? So like we sent this token to someone a while ago, and they've just made a request to like quiz delete or quiz get details, and they've sent us this token with this information in it, including this signature here. Okay, that makes sense. And what I can do if I would like to verify that this is correct is what you do is you basically go, you print out, I can print out the input token signature, but then what I also print out is I print out the input token's session ID combined with the secret that I have to hash. Does that make sense? Probably not. A little bit. Some yes and some no's. So I've got the signature. That's just me printing it out on the terminal. But now I'm printing out the session ID plus the secret hashed, and I see what happens. And it turns out that there's a problem in my code. Where's the problem? Is it at the bottom? It is at the bottom. Ah, look at that. They're the same. That makes sense. However, pay attention to this. What happens if I now, as a bad person, before I send that to the server, decide to change the session ID to something else? I'll change that to a 2 now to try and tamper with it. But what happens when I send that and I tamper with it is I get a different hash. Because what this is basically like me taking a snapshot and saying, I'm going to take that token as it is, or that session ID, I'm going to combine it with something that they don't know, and I'm going to get an irreversible output over here, which is basically a snapshot of the correct data. So if they go and tamper with it, when they give it back to me, I try and take another snapshot of that data, and it looks different. I've seen that something's changed. It's a little bit heady. What this is this is actually an implementation of JWTs. I introduced this into the course really early on, and we did it for a couple terms, and then I got rid of it because I thought it was confusing students, but I've slowly been kind of chatting about it more. I think that trying to understand it just from this website is really confusing, so I've just taken you through like the journeys, and I'm not going to show you this, but a JWT is basically a formalization of what I've just shown you. It's a way of kind of tamper-proofing data by doing that exact process. You don't have to worry about that website. But the point is like, and you imagine now I'm the person who tampers with it. I think, oh man, okay, I've just changed the session ID from 1 to 2. The signature's probably not going to work anymore because I've changed the data. So I need to change the signature to match it. But how do I generate the new hash? I don't have that secret here. This secret's like the kind of the key to understanding this, because the secret is known by the server and no one else, right? Like it's known by your server that's running, but it's never known to the person on the internet using the web browser, the API client. And because they don't know the secret, they can never generate that hash correctly again. So you've relied on the fact that only you can generate valid hashes, and you've sent that to them so that if they send something back, you're like, it's been tampered with. And this is used really heavily in basic, like this is used all the time on the internet these days. And it's how, like, if you're on a website, quite often, and it's important because quite often when you send a token to the web server, it's more efficient if the token actually contains the information. So the power of this method is that it's useful when it's not in your interest to hide data from a user, right? But it is in your interest to make sure they don't change it. So that first topic that we spent 2/3 about was like, how do we, for information that we never ever need to see on the server, how do we protect it? We hash it. Pretty straightforward. This one, a little bit more complicated. It's saying for information we don't want to hide, such as session ID and user ID, how do we tamper-proof it? Again, you can do what we talked about early on and just like make it a really big random number. That just reduces your surface area of a problem by 99%. Or you can implement something like this or look at JWTs and whatnot. The cool thing about this whole topic today is that it's completely non-blocking for your entire iteration 3. It's totally tangential. So like, it can be worked on day 1, it can be worked on week 10 Friday. It doesn't really matter as a topic. Like, it's totally independent. It's not blocking anything at all. But again, summary, you need to hash your passwords, pretty simple. You need to make things tamper-proof, which could be anything on the range of like really like the lowest effort, which is still fine, which is make your random numbers bigger, or it's like hash your incremental numbers or make your incremental numbers bigger. Or if you want to be like more adventurous and kind of challenge yourself a bit, which I would encourage because it's quite an interesting topic that's worth getting your head around, then you do something like this where you basically include a signature or something similar to like totally lock it in. You can have a look at this if you'd like to. It's one of those things where like this will make writing the code easier, but you'll have to spend the time to like digest it, though it's not particularly like difficult to understand. This is like you'd sit with it for 15, 20 minutes and go, oh, okay, I see how that is. It's kind of that thing Hayden talked about. But yeah, basically, I really don't want to talk about it too much, but basically what happens is, this is why I removed it from the course a little while ago. It's too heady. You can look at it fine. Like you're more than capable enough, but I think this is totally fine. And since you're already implementing hashing, it's not particularly hard anyway. Like the code's like 3 or 4 lines. In the big world, if you tried to do this yourself, someone at work would like knock you across the head and be like, "Why are you doing that yourself? Why don't you use like industrial scale libraries that like people have perfected and open sourced and critiqued?" But for the focuses of this project, I'm generally kind of like, yeah, go play around with it, because at least you'll have a bit of a tactile understanding of what's going on, because like every time after this, you would never actually get this low in detail, if that makes sense. Yeah, so that's pretty much it. Authorization, we kind of talked about at the start, so we don't need to really go into too much detail about that. Yeah, that's it for that.